Hello and welcome to lecture 25 of chapter 19 in our comprehensive course on AI, ML and DS. Now here we want to discuss about fourth statistical test which is used for hypothesis testing, that is ANOVA. It is a short form, analysis of variance. So analysis means AN of O and variance means VA. So that is how the name ANOVA was decided. It is used to compare the means of three or more groups. Now this is a totally different thing than t-test or independent t-test or paired sample t-test or etc. Here any number of different groups can be taken and you want to compare whether before some intervention or after some intervention or before doing something and after doing something are the means different. Okay, some examples are these. One is this: comparing the average accuracy of three different machine learning algorithms on same data set. So data set is same, but you do, what is that something which you are doing? You are training your data set and doing all that process, train, test, split, and then making machine learning model. So you have made machine learning model on my data set using logistic regression. Then I make another machine learning model using random forest, and then I make another machine learning model using SVM, right? So in that case, the question is that which model should I use later on? So for that, you have to perform a statistical test like ANOVA and find the average accuracy for this model, average accuracy for this model, random forest, and average accuracy for the third model, that is SVM, right? Okay. And so if you do that, now when I say average accuracy means you may do say 10 runs of logistic regression. You may run 10 runs of random forest and 10 runs of SVM, or even if you do only one run, but we have earlier done that 5-fold cross validation and etc. So you know that internally whatever result of logistic regression accuracy is displayed to you, that is actually the result of several different experiments conducted internally by the algorithm and using first fold, second fold, third fold, etc. Or first fold as a train set and the remaining 4 as a test set, then second fold as the train set and the remaining as the test set, and third fold as the train set and the remaining as the test set, and all accuracies are counted and finally their average is found and you are getting the average accuracy as the output, right? Now again, here also what will be the null hypothesis? Then the null hypothesis is that changing the algorithm from one to another on the same data set does not have any effect on the average accuracy. So that means status quo, all models will have same accuracy, but alternative hypothesis is that at least one model performs differently. Either it has a very big improvement in accuracy or it has a statistically significant deterioration in accuracy, but all models do not perform equally. Okay, then for that you can use one-way ANOVA test. Then similarly here, second real life example is there. Suppose you are running a gym and you have total around say 20 clients or 27 clients, and you want all of them want to lose weight and you want to try 3 different diets on them. One is a low carb diet, another is vegan diet, and another is Mediterranean diet, and you want to see that which diet is having more effectiveness on the weight loss. Okay, so then for that again null hypothesis will be all diets are having equal effectiveness, or the mean weight loss for all the 9, so you divide your 27 clients into 9 will be put on low carb diet, 9 will be put on vegan diet, and 9 will be put on Mediterranean diet, and you find the mean weight loss. Then the null hypothesis is that mean weight loss will remain same, while alternative hypothesis will say that at least one diet will result in different mean weight loss. So maybe say Mediterranean diet will have highest weight loss, or maybe low carb diet will have highest weight loss, but at least one diet is more effective for weight loss compared to the other two, right? And here also there is 3 algorithms are taken, but you can take 5 algorithms or 20 algorithms. ANOVA has no limit of how many groups you can compare, 3 or more, right? So that is the greatness of ANOVA, and that is why ANOVA is always preferred, right? Now this real life example we did. Now this machine learning example, right? So a data scientist wants to evaluate effectiveness of 3 machine learning algorithms based on their average accuracy across 5 data sets. Now here actually it is just slightly different than this. Here there was same data set and you tried on this logistic regression and all that 3 algorithms. Here you are trying different machine learning algorithm and you are taking data sets also different, but same 5 different for logistic regression. Then you try same 5 different for decision tree, and you will find same 5 different for random forest. So that means it is a little bit more rigorous way of testing, that when you say the one particular algorithm random forest is more effective than the other 2, then is it more effective for all variety of different data sets? One may be having different data distribution, another may be having different data distribution. So that is what we are testing by taking different data distribution of 5 data sets, and all 3 algorithms are subjected to all 5 data sets. And null hypothesis says that average accuracy is same for all the 3 algorithms, while alternative hypothesis says that at least one algorithm has different accuracy, right? And again, we will use one-way ANOVA. Now here, we want to take this example by code, that is the testing the effectiveness of three diets. Okay, so we will create some synthetic data of some sample, and then we will divide the data into three parts, and some will be subjected to low carb, some will be subjected to vegan, and some will be subjected to Mediterranean, and then we will see that. Okay, so here we will find that in this code. Now you can see that we will get the same code for most of the lines. NumPy is imported, Pandas, Matplotlib, and Seaborn. Only this line is news from scipy.stats import f underscore one way. F test it is often called. So f underscore one way, that is one way ANOVA, right? Now generate synthetic data set with this random set. So let us take some data set for weight loss for low carb diet, weight loss with vegan diet, and weight loss with Mediterranean diet. So first data set has mean of 5 kg, mean weight loss 5 kg, and standard deviation 1.5 kg, and total there are 30 observations. Second data set has mean weight loss 4 kg, standard deviation 1.2, and there are again 30 observations. While third diet had mean loss of 6 kg with a standard deviation of 1.3, and there are 30 observations. So we will create this data set, and we will combine, these are just NumPy arrays, right? So data distributions, but then we will combine them into a data frame. So diet type will be one column, and there you will write low carb, this multiplied by 30, plus vegan, this multiplied by 30, plus Mediterranean, this multiplied by 30. So this will become your one particular column, and then weight loss will be equal to np.concatenate. You are using concatenation of this weight loss columns. So weight loss are given, mean weight loss is 5, 4, 6. So based on which some weight loss will be created in each row, and then you will do the concatenation of that. I will show you the data, then only it will become more clear, right? So this is the data which we have generated. The top 30 rows, they are for low carb diet. The middle 30 rows, which are not visible because only top 5 and bottom 5 are seen, that are for the vegan diet, and the bottom 5 rows here, which are visible, are bottom 30 rows. They will be for Mediterranean diet, right? And this is the weight loss which are randomly created by this kind of distribution, with this much mean and this much standard deviation for low carb, with this mean and this standard deviation for vegan, and for this mean and this standard deviation for Mediterranean. So this is the data which we have created. Now perform the one-way ANOVA. Okay, so low carb data equals data. From data, you take only the data type column and compare it with low carb. Okay, so first what I am doing is, this is one combined data frame. I want to split this data frame into 3 parts. So I want to take the whole low carb portion separately. So that is done by this line of code. Okay, so low carb data equals to data from the entire data set. Take this column for conditional checking, data diet type, and compare it with this value, low carb. So that means for the top 30 rows, this condition will be matched. Okay, and also take other column, weight loss. Similarly, for vegan data, again take the entire data set, take this column, data diet type, and match it with another vegan. Okay, so vegan value is not there, but here this is a comparison operator, equals. So that compares the diet type with vegan, and that means it will create a subset of this whole data of only those 30 rows where diet type is vegan, and it will also take the weight loss column for that, and Mediterranean similarly. So if I here also print this 3, then you will get more clear idea that now what we have got. Okay, so low underscore carb underscore data, then vegan underscore data, and then it is underscore, and Mediterranean underscore data. Okay, so let us print them. This step I am still taking in the next cell. Okay, so and here I think I will have to write print also, because if I want to print multiple things, then if I don't write print statement, then the Jupyter will only print the last, and the previous 2 will be overwritten by the last output. So only the output of the Mediterranean will be seen. That we know, but a good reminder after so many chapters if some of you have forgotten. And with VS Code etc., you will have to provide that print statement, right? So this is for first, which data? This is low carb data. Only mean weight loss is kept. This is second data, that is vegan data, and this is the third data, that is the Mediterranean data, and you have kept only one column, that is the weight loss column, right? So you took subset and you got 3 data sets. Now you compare those 3 groups. So this is one group low carb data, this is another group vegan data, and this is another group Mediterranean data. You apply one-way ANOVA test to see if the mean weight loss for this group and mean weight loss for this group and mean weight loss for this group are significantly different or not, right? And just like t-test gives t-statistic and p-value, similarly ANOVA is also called f-test and it gives f-statistic and p-value. Okay, so then you can find that f-statistic and p-value, and you can decide based on that. F-statistic is coming out to be pretty large, and that means p-value, its chances of being very, very small is high. So here it is so small, maybe 0.000000005, like that. So it is so small that it is almost zero. Now our significance level is this only. So we know that if p-value is less than alpha, here my p-value is less than this value, right? It is very, very small. So in that case, I will reject the null hypothesis. But what was my null hypothesis? Null hypothesis was that there is no difference on the diet, or in other words, that means the mean weight loss remains the same for all diets. So I started with that null hypothesis that okay, this diet will also cause weight loss, this will also cause weight loss, and this will also cause weight loss, and all three will cause similar weight loss. So that means whether you use this diet or this diet or this diet does not make any difference. Okay, mean weight loss remains the same. That was my null hypothesis. But here what I got, p-value 0, or that means nearly 0. So then p is less than alpha. So that means I will enter this part and I will reject null hypothesis. So alternative hypothesis would be accepted. And what is that alternative hypothesis saying? It says that at least one diet is resulting in different mean weight loss. Okay, so that means that you can at least be sure that there is one out of these three diets which is proving to be more effective, right? For it is causing different weight loss, maybe higher weight loss. Now the question is, which one is that? So for that, these visualizations really help. So here we, as usual, plot one box plot, one bar chart for mean weight loss, and one pairwise scatter plot for additional insight. This pairwise scatter plot is just like what we used to do in scatter matrix, that is pair plots. If you remember, if you put a pair plot of a variable with itself, then it gives a histogram, and the rest of the thing are scatter plots, right? So then this kind of plot will be obtained. Let me show you, and then confusion, if you are confused, then confusion will be removed. So this is the box plot first. So the box plot clearly shows that the median weight loss for the vegan diet is the least. It is below 4 kg. Median weight loss for low carb diet is somewhere 4.5 kg, and the median weight loss for this Mediterranean diet is significantly above these two, and that is 6 kg. So it seems that the Mediterranean diet is the most effective for weight loss, right? There is some outlier also that you can see in this data set, but that is okay, just one or two outlier points. Here also you can see the same thing. You are finding the mean weight loss for each of the diet point and showing them by bar chart. Then you will see that low carb has around 4.5. That is the same as this, okay? But I think that was median, right? This is mean. So this is 4.5. This is around 6, and this is around less than 4 kg. And it is a normal distribution. Perfect normal distributions are there. So therefore mean and median are here same. And this is that pairwise scatter plot for different diet types. So it is weight loss versus weight loss. That is what I said, that if it is the same parameter versus same parameter, then the scatter plot turns out to be just a distribution plot. So red color, that is the here vegan diet, and therefore its median will be less. So if I draw a vertical line from the peak somewhere here, then its median will be at 4, okay, less than 4. Then green color is for Mediterranean diet, and therefore its median is higher. No, I think here the color code is changed, because otherwise the median weight loss for this diet should be highest, no, Mediterranean. So I think the green is here for low carb diet, and for that the median weight loss is somewhere less than 5 but above 4. So that is low carb diet, less than 5 but above 4, right? And green graph, and this graph, okay, so that is this graph here, that is for Mediterranean diet, and that shows that the median weight loss is the highest. It is above 5, in fact 6 kg, and below 7.5. So median is above 5 and below 6 kg and below 7.5. So I have concluded that my null hypothesis is wrong. Null hypothesis was that there is no effect on the weight loss by changing the diet, right? So mean weight loss remains same whether you go for this diet or whether you go for this diet or you go for this diet. But I have found that p-value is nearly 0 or less than 0.05. So I reject null hypothesis and I accept this hypothesis, which says that at least one diet has a much different weight loss, statistically different weight loss compared to the other two, or all three may also be having different weight loss with respect to each other. Okay, but that is fine. Here, if this is taken that way, that one has different weight loss, but which one is that, and which gives the best weight loss? So for that, you have to either find the mean of all these samples, that is this low carb, its mean, okay, Then this legend data, its mean, and Mediterranean data, its mean. You can find the mean of all this and then decide which mean is highest, or you can plot it. Then plotting will show it in nice visual manner that Mediterranean diet is the most effective diet, right? So this is explanation of the code and explanation of visualization, which you will read because now it is already explained to you. So next lecture we will talk about is about chi-square test. So this lecture is over. We will see in next lecture about chi-square test.